Greetings to all you exquisitely inquisitive ladies, gentlemen, and scholars, and welcome to Philosophiae Naturalis with Jayallan. In this episode, we shall be deriving related rates. In particular, related rates as it pertains to the expansion rate of a contrived universe within its infancy. However, in order to understand rate of change, we first must understand implicit differentiation. Here is a simple implicit differentiation problem for us to solve. So you take the derivative of x squared, which will be 2x, right? Simple enough. And then you add, and you take the derivative of y squared. However, this is a little weird because we're taking the derivative of y squared in terms of x. So we're going to have to add something on to the y squared. So the derivative of y in respect to x is what we're doing here. So we have to use the called the chain rule and add on the dy dx to the 2y. And then we take the derivative of 25, which it's a constant, and the derivative of any constant is simply 0. There we are. So what we want to do next is isolate dy dx, solve for dy dx. So we'll take y dy dx equals negative 2x. And then we divide the 2y from both sides. We end up with dy over dx equals negative 2x over 2y, which will simply end up equaling negative x over y. And that would be our answer. So dy over dx equals negative x over y. Isn't it interesting how we started off with these two variables and we ended up with the third variable that we wanted to solve for. And that's how implicit differentiation works. Now on to rate of change. Okay, so here is a very exciting situation for us. Performing an experiment at CERN labs in Switzerland, you accidentally create a spherical universe that will swallow your universe if you don't act quickly. You slow it down, but the volume continues to expand at a rate of 100 cubic meters per second. How rapidly is the radius of the universe increasing when the diameter is 50 meters? Right, so how we're going to perform this? First, we need to look at what we have here. We're given a rate of change of 100 cubic meters per second. So that is the rate of change of the volume of the universe as it's increasing. What we don't know and what we need when we're looking at related rates is we know that we need at least two related rates. We have this related rate, so where's the other related rate? We don't know what it is, but what it's asking for is, it says how rapidly is the radius of the universe increasing when the diameter is 50 meters. So it's asking how rapidly, rate. It's asking for a rate. How rapidly is the radius of the universe increasing? So that's the rate. Rapidly, radius changing. The radius is changing. How fast is the radius changing? So we need to know the rate of change of the radius of the universe. So here, dv over dt equals 100 cubic meters per second. So that's saying we know that the rate of change of the volume as it pertains to time, dv over dt. So we're doing this in respect to time. That time is the dependent variable. V and R are our independent variables. That's what we need to solve for. So dv of dt, we already know what dv is. It's 100 cubic meters per second. So we don't really need to solve for that. What is dr dt? The rate of change in respect to time. That's what we need to find. Dr dt, we need to know what the radius is. We're given diameter. That's to sort of throw you off. What we really need, what it's telling us really, is that the radius is 25. Because the radius, as you should know, is half of a diameter. The radius is 25 meters. So we need to know the rate of change of the radius in respect to time when the radius is 25 meters. Rate of change of the radius in respect to time equals, we don't know, at a radius of 25 meters. So again, we're given the information on the rate of change of the volume. So what we're dealing with is volume. Volume of what? Of a spherical shape. The spherical shape of this universe as it expands. So we need to think, what is the formula for a sphere? That is right, so we come up with the formula for the volume of a sphere, which is this is just something that you should have memorized, or if you don't have it memorized, you just need to look it up. It's not something that we can just derive from this information here. The formula is this: volume equals 4/3 pi r cubed. What we need to know is the rate of change of this formula here. So we know that rate of change is when you take a derivative. We also need to know that we're dealing with an equation here with multiple variables. The v is a variable, and the r is a variable. The pi is simply a constant. It's not a variable, of course. So we're taking the derivative of two variables in respect to time. So we're going to end up doing implicit differentiation twice, actually. So the derivative of v is 1, because the derivative of a variable is always 1. But we're taking that v, volume, in respect to time, so we need to use the implicit differentiation rule for that. And then we take the derivative of r, cubic r, so we bring the 3 down in front of the pi, and we multiply that 4/3 by 3, which obviously the 3 will just cancel out, and we're left with right, so the 1 multiplied by dv dt just becomes dv over dt, of course, and because the 3 cancels out, we get 4 pi r squared, and then because we're doing implicit differentiation, because r is in respect to t, so we have to do the implicit rule there, dr of dt. Now where do we go from here? Well, we know what dv dt equals, right? We know that the rate of change of volume in respect to time equals 100 cubic meters per second. So in replace of this, we can just plug 100 cubic meters per second into that, and we know what the radius is. So we're looking for the rate of change of the radius at a radius of 25 meters. So the radius will be 25 meters. So we have 100 cubic meters per second equals 4 pi times 25 squared dr over dt. So we want to solve for dr over dt, right? We want the rate of change of the radius in respect to time. We want to know what that is. So we're going to solve for that. And so what we do is we simply divide this by both sides, and we bring it over to here. So we have 100 cubic meters per second divided by 4 pi 25 squared. And then you just plug that into the calculator. So we find here that the rate of change of the radius with respect to time at 25 meters is 0.0127 cubic meters per second. So it's slowed down. Hopefully you can make it stop completely, or we're all going to perish in terrible, horrible agony. And so that concludes this episode of Philosophiae Naturalis. I hope that you enjoyed it as much as I did, and I'll see you next time.